We need the reactions at A and at the roller at C. We can break it down into two pictures, the beam that goes from A to B, and then that's pinned together to the second beam from B to C. Or we could take that external picture, but as we saw in Chapter 6, I tend to just break it down to the individual pictures right away. So I'm going to start by breaking it already down and looking just at AB to begin with. At A, we have another cantilever connection, so we'll have an AY, an AX, and an MA. At B, we have a pin connection to the other beam, BX and BY, I'll assume. And here we have to be careful with how do we model that distributed load onto this free body diagram. So this is where we have to look at how much of the beam are we actually considering. We're only considering this 3-foot section that goes from A to B, where it's then pinned together to the other beam. This section only sees, I'll draw this temporarily up here, this much of the distributed load on it with a constant value of 500 pounds per foot. This section of beam doesn't know anything about the amount of the distributed load that goes from B to C directly. It doesn't see that weight directly. It will be influenced through the BY, BX values, but it only knows that this is the distributed load that's acting on it. So for this picture, the only external force that will be acting is from this amount of the distributed load. So the intensity, the constant intensity of 500 pounds per feet over only 3 feet, even though the entire distribution goes over 9 feet. In this picture, only the 3 feet that touch this beam are going to be used. So the equivalent force from just this amount of it will be 500 pounds per foot times 3 feet. So this beam only experiences 1,500 pounds of that total amount, and it will act at the center of this amount of the distribution, the 1.5 feet. The distribution does go on, but this beam doesn't know it directly. BY would include that information, though. I have 5 unknowns in the picture, AX, AY, MA, BY, BX. I'm going to draw another free body diagram that will hopefully make the algebra a little bit easier in the next step. So picture 2, I'm going to draw the second beam that went from B to C. We have a pin connection at B. We've already made the assumption of what the directions were, so I must make it equal and opposite in picture number 2. The roller at C will have just a vertical reaction. And the beam from B to C only touches the distributed load directly applied on it. So it happens to still be the same intensity uniform load. So it will be a 500 pound per foot load over, for B to C, it goes over 6 feet. So in this section, the total area will be 6 times 500 pounds per foot. So 3,000 pounds will be the equivalent force for this segment of that distributed load. And it will act in the center of this part of the beam, so 3 feet from either end. Between the two pictures, I now have 6 unknowns, 2 rigid body problems, so I can get 6 equations out of them. So it should be a solvable system. Now it looks just like a Chapter 6 question when we have frames and machines. If we look at free body diagram 2, there's only 3 unknowns in that problem, so that's going to be a better place to start solving this. So I'll start with the sum of moments around C in picture number 2. I'm going to have the 3,000 times 3. Plus 6BY. For BY, I'm going to get negative 1,500 pounds. the forces in the y in 2, I'll get minus by plus the cy minus the equivalent loading, the equivalent force from the distributed load, 3,000. So cy must be positive 1,500 pounds. Finally, the x direction. The only thing in the x direction I have is the bx. So the bx must be 0. And it's really negative bx, but still 0. Going backwards to picture number 1 now, I can take the sum of moments around A to start. I have the couple from the wall on the beam, so I have the MA that I assumed was positive, minus the equivalent force times its equivalent distance from A, so 1,500 times 1.5, plus 3 times BY, which I have found previously, leaving the only unknown to be MA, so the couple from the wall on the beam, I get 6,750 pound-feet. In the x direction, I'll have the ax plus the bx. I already know that bx is 0. So ax must also be 0. And at last, if I find the forces in the y direction in picture 1, I have my ay, I have my by, minus now the 1,500. So the value of ay must be 3,000 pounds.